My name is Bob Van Det, and I'm the architect for the JavaFX embedded product at Oracle. We're going to have a nice intimate setting today. This is a repeat of my talk that is actually scheduled for later in this week. That got scheduled only like last week, so this Thursday is going to be a lot more people attending, but we'll have a nice intimate setting here. So I'm going to cover JavaFX embedded, just a couple of slides just to review for those folks who may not be familiar with the product. I'm going to spend 2 slides on that and talk a little bit about where we're going and how we're going to reduce the size of the product to make it more adaptable to lower end embedded devices. I want to talk about how we're going to modularize the SE embedded product with compact profiles, some new tools that we're using to give you more flexibility on how to build your custom embedded runtimes. We have a new graphics stack, which is really exciting, that I want to talk about in a little bit of detail, but there's actually a full talk later this afternoon that I'll go mention. And I'll talk about our roadmap even beyond JDK 8 and the plans for Jigsaw and JDK 9 modules and how that's going to impact embedded. And I've got a couple of demos that I'll give you along the way, and hopefully it'll be somewhat entertaining. So let me just give a quick review of what is JavaFX embedded. JavaFX embedded is a full Java standard edition implementation that has been customized to reduce the amount of footprint required. If you take the Linux x86 Java runtime, it's about 140 megabytes today if you download the binary and you explode it onto your file system. We've actually taken the x86 version and we've gotten it down to 42 megabytes. So that's a 60% reduction in disk footprint. We've also reduced the memory requirements down that SE normally needs. We've reduced the memory usage down to the point where you can run it in 32 megabytes headless and 64 megabytes head full. We have on our web today, we have 2 configurations for each of our supported architectures. You have a binary that you would download for the headless and one for the head full for ARM especially. And of course we need embedded uses different architectures than typically are available for JavaFX. We have ARM, PowerPC, and the reduced version of the x86. And it's full JavaFX compatibility. We pass 100% of the TCK, and it's available today. Here are some of the unique platforms that we support. We support ARM version 6. There are different architectures and chips for ARM and PowerPC, and we have to provide different binaries for binary compatibility on those architectures. We support ARM version 6, ARM version 5 headless with different floating point options for soft floating point, ARM version 6 headless and headful with the vector floating point unit. And just this year we've released the server JIT for those customers that are trying to target the server market with the ARM low power processors, multi-core processors. So that now allows you to use both our client JIT if you'd like for smaller embedded and server JITs for high performance throughput and server applications. We have 2 PowerPC implementations. I want to make it's a little bit confusing if you are looking out. You see E500 MC versus E600 chips. We support standard book E with classic floating point with this E600 release. If you're using the Freescale E500 MC, don't be confused with E500 V2. You actually have to use the E600 version on the E500 multi-core platform that Freescale is offering. That's because when they went to the multi-core chip, they switched back to classic floating point, the traditional IBM defined floating point instruction set. But if you use an E500 V2 core for your device, you need to use the E500 V2 specific binaries because it uses the embedded floating point, the auxiliary processor that Freescale has defined. And finally, for x86, we have a headless version that is much smaller, as I mentioned, than the standard SE binaries. So going forward to JDK 8, what are we doing to try to crunch down those binaries even smaller so we can get into lower end devices? We are converging the best features of the ME CDC product and SE and providing a JDK 8 compatible implementation. We're going to bring the critical features of CDC to SE. One of the major benefits of CDC was the fact that it's much smaller and can fit in much lower end devices. And in order to achieve that goal, we're going to get our static footprint down to 10 megabytes. And we're also reducing the memory even further than we've done with SE Embedded, the version 7 today. We're getting it down to 16 megabytes for headless applications and 32 megabytes for headful. And as I mentioned earlier, we have a new embedded FX stack that is going to provide an alternative stack to Java 2D, Swing, and AWT, which does consume a considerable amount of memory and disk footprint, static footprint. So how are we going to get there? We're going to reduce the size of the VM. Today we have, for ARM, we have a client VM, we have a server VM. We're now going to add a third VM to the mix, which is really just a specific modularized version of the client VM, and we're going to get that down to less than 3 megabytes. This 3 megabytes is actually the target on x86. On ARM, we're hopefully going to get that down to even less, like 2.5. We're going to try to get it down as close to 2 megabytes as possible, but our high watermark for all of these platforms is try to get it down to 3. We're also reducing the amount of memory that's used by the JIT. We're doing some tuning so that the JIT memory consumed by embedded applications will dynamically adapt to the underlying platform and alter some of the JIT characteristics so that we reduce the size of the JIT code. And we're also going to try to eliminate and remove JITted methods that are no longer used so that we can keep that memory as small as possible. And for more memory reductions, we're actually taking the class metadata. As you load classes into memory, we create C++ objects for these classes. We're actually taking fields out of those classes that are not frequently used. They're used maybe for serviceability or debugging or profile monitoring or symbol table resolution. And we're putting those all into auxiliary data structures so that we don't have to allocate them for the most frequently used product versions of your application. And since we're merging all of these features into the standard hotspot virtual machine that's used for servers and x86, Spark, and 64-bit, all of the features that the hotspot team is doing are going to be available for our embedded application. This new JSR 292 work, Invoke Dynamic, which allows you to run different languages on top of the virtual machine. They're moving the permgen out of the heap so that we can have better management of that metadata, so we can free it much easier. We don't have to do garbage collection in order to free up class metadata, and that even helps us in the embedded market. We're doing NMT, which is native memory tracking, to give us a better idea of the memory usage of the VM. It's been very difficult to find out how much memory beyond the heap that the virtual machine is even using, and this new technology is going to allow us to do that. And finally, we'll have finer grain, better control on compiler jitting. We'll be able to specify, specific methods or subsets of methods that we want to compile or we don't want to compile. So we're doing a little bit better job in that to give you better control over what you want to compile. We always are pushing the envelope, trying to get better performance out of the newer ARM processors and newer PowerPC processors. That work we do in every single release, and we'll continue to do that for JDK 8. And finally, we're adding additional serviceability, which we haven't had for ARM and PowerPC. There's a serviceability agent which allows you to do better diagnosis of crashes and seg faults. The serviceability agent will now be available on those platforms. So how are we going to get even small down to this 10 megabytes? So we got the VM down to 3. So that means we've got 7 megs left. So what are the biggest consumers of that additional disk static footprint? Well, the class files, of course. rt.jar is 50 megabytes in the standard release. We've compressed it down to 25 megabytes, but we need to get it down a lot smaller. So how are we going to do that? We're actually going to define different profiles for SE8, which will be subsets of the full SE. The benefits of this is we'll have a smaller headless runtime than we can even achieve today with SE Embedded. We'll have a new graphical stack that will only consume 6 megabytes. All of these things will contribute to a quicker download, quicker startup time for your application. And this is the basis of our ME and CDC converged product. For those of you that are familiar with CDC, this is similar to the foundation profile, the small set of classes that you can use to run an embedded device. And here's a picture contrasting the existing SE Embedded full JRE on the right, where we have the VM and all the base classes and the UI toolkits. On the left, we see that we will have 3 different profiles which will build upon each other. We will have our new smaller VM for the smallest compact profile, and then we'll have the base set of classes which are equivalent to the foundation profile for CDC. We're calling these things for now compact 1, 2, and 3, But as we go through the JCP and the expert group for the JDK 8 specification, these names will undoubtedly change to something a little bit different. But we're using these simplified words for now. The next level, Compact 2, will add additional functionality. These are things like the optional packages that you might have found in CDC, RMI, JDBC, etc. Compact 3 adds the rest of the APIs that we think will be applicable to an embedded device. And finally, we'll have some optional components that you'll be able to add to any one of these tiers. That's things like our FX stack, some optional security providers, etc. Here are kind of our current estimates of where we think we're going to be with the sizes of these different profiles. For the Compact 1 profile, where our goal is to get down to that 10 megabytes. Now, JDK 8 isn't done yet, and the Lambda team is still adding more stuff in, and we're still trying to pull stuff out. So this 10 megs may be 10, 11, but our goal is to try to get as close as possible to that 10 megabyte limit. Compact 2 profile, we think we're going to require 7 more megabytes to add the functionality in it. 24 megabytes for, this is our new headless JRE, where we've totally eliminated Swing, AWT, Java 2D. In our headless SE embedded today, those classes, unfortunately, are still in there. Because to pass the JCK, I need to throw a headless exception when somebody tries to create a Swing frame. So I have to carry around all those classes just to do that. So there's a lot of dead code in there that we're finally able to eliminate. That allows us to get half the size of our SE embedded headless release in this Compact 3 profile. So the SE embedded headless today is 43 megs, I believe, something like that. So we're almost half the size, which is going to be great. So what's in the various profiles? As I mentioned, Compact 1 is equivalent, roughly equivalent to the CDC profiles. We have the basic Java Lang, I/O, NIO, text processing, math, the networking APIs. We're adding logging in here because we've had a lot of requests from the embedded folks when I sent information out requesting, what other things would you like to see in it? They wanted logging. And of course, Java has to have the security classes in there. Now, Compact 2 has all of the packages that are in Compact 1, but we're adding a few additional packages similar to the CDC optional packages. Java SQL, we're adding JDBC support, RMI support, transaction APIs are going to be added in the Compact 2 profile. Compact 3, we're adding a lot, pretty much everything else that's in the standard SC set of packages today. We're adding management support, the row set APIs, which are not as frequently used in the SQL. The bottom set of classes are the compiler APIs. So we want to be able to enable folks that want to make little web servers that want to possibly run Java C to compile their classes. They'll be able to do that at the Compact 3 level. The preference API and scripting languages. These are all the things that we're going to be adding to Compact 3. And finally, we'll still be offering the full JRE for those customers that want to use the remaining classes that we've eliminated from the Compact 3. Those things are things like JAX-WS. For large web server, we figured these, if you're building a web services server, you're going to need a lot of disk space, a lot of storage for your classes. You're not as concerned about size as some of the lower tiers APIs might be. We've eliminated the desktop APIs. All of the Swing, AWT, Java 2D, and imaging APIs are all out of Compact 3, and you need the full JRE in order to support those. And Corba is finally out of the embedded JRE. Yes?
Can you go back to that one slide?
Which one?
Just
one before?
Yeah, down, right.
Okay. These slides are available, will be available on the web, and they're actually available right now.
Oh, okay.
If you just go and search for my name, and there's actually one tab you can click on for all the presentations, and it's up there, it's posted, so you don't have to take notes. So we're going to, as I mentioned, we will have some optional components that you can install on any one of the profiles. The FX embedded graphics stack that I'll get into more details can be added on top. Localization support, by default we'll put US only, but if you want to put all of the rest of the locales, you can add those in, and of course at the cost of additional footprint. We will have some optional security providers that are less common security providers, things like the elliptical cryptography and PKCS11, which isn't even used on the Linux platform. And if you want to add debugging support, we will allow you to add debugging support to any one of the profiles so you can run JVMTI and debug your Java applications. So what are we doing in terms of helping developers to get ready for profiles? Well, we're planning on enhancing Java-C with some options so that you can verify whether your application at the source code level will be compatible with one or more of the profiles. So when you run Java-C, we'll be adding a new option, -profile, where you can specify compact 1. And if you're compiling your Java code and it's using a class that's not in compact 1, you'll get an error warning you that you either have to rework your code to eliminate that or bump up to the next profile level. We're going to add a new jar option, which will allow you to specify which profile you intend your jar to run on. It will mark the jar file in the manifest with the minimum required profile. We're only going to do this for the main jar application, since some developers may bring in third-party jar files and they don't, they have to not necessarily know what profile it might run on. We're also going to provide some tools that you can run on a jar file to tell you which profile this jar file requires. And finally, during the loading of an application, we will be verifying that the current profile it's running can actually run the jar file that you're pointing us at. And finally, we obviously have to give you a way to figure out what profile you're running with Java-version. And I'll show you that in a demo.
Hey Bob, any plans for like Eclipse and NetBeans type module support where you can have these sort of profiles defined?
Well, I probably should have put this in here, but in the Java docs, we're planning on having, you can uniquely identify which method is in, if you go for a method, it'll tell you whether or not it's in compact 1, 2, or 3. We're talking with the NetBeans folks about how to hook that in. We're going to be providing like a ct.sim, which will allow them to tell which profile, but they're a separate team, and so we have to go kind of negotiate with them to get that done. So the download image is going to be different than what you're used to today. Instead of having a headless bundle that you download and you install, or a headful bundle for ARM, we're actually going to put all of the profiles into a single package. And we want to give you the flexibility to pick the features that you need and the size you need, rather than us making the decision for you. So we're going to provide this tool called JRE Create, which you'll have to run if you want to create your custom embedded image. In this package that you download and expand, we will have one per architecture. There'll be an ARM v5, ARM v7, and eventually the hard float for the Raspberry Pi users. But inside each individual download will be the 4 different profile levels. There'll be compact 1, and I should have put 2 there, 3, and the JRE, and any of these extensions that I talked about that you could add on top of each one. And you would then run JRE Create and provide it with some input, and it will select from those different profiles the binaries that you've asked for, and possibly modify those binaries based on these options that we're providing you, and it will generate the profile, the JRE that you want. And some of the things that we're going to allow you to do are to include Java debugging support, and that means this. In order to strip down the JRE as small as possible, we're going to pull out all of the symbolic information, line number table and symbol tables that are not needed to run an application, but they take up space. And so by default, if you ask for some of these smaller profiles, we're going to strip out as much as we possibly can to get it small. But you can put it back with this option. The -D, the destination, just specifies where you want to write the output to. JDK home will default to where you're running the JRE Create from, but you might want to pick a different one for different versions. If you want to we strip out the debug information. This is the debug information from the stripping. If you want to keep it, it's -K. -G says, I want JVMTI support. Please add it to my runtime. I mix those up. Dry run will actually not produce the output. It'll just tell you how big this is going to be. -P or -profile, this is how you tell it which profile you're interested in. The target architecture is for a future. If we want to bundle all the ARMs into a single package, we would have Linux ARM, soft flow, VFP. You will be able to pick which architecture you're going to target. And this --VM is where you'll be able to pick amongst the 3 different VMs. We have this minimal small VM that's the 3 meg, the client VM, and the server VM for those architectures that support it. We don't have a server VM today for PowerPC. And the extension option is where you'll be able to say, I want the FX support to be added to my package. I want one of these security providers of the locales I want to add. This is how we're going to allow you to select those. So here's a couple of examples of how you run this tool. You use JRE create -d or --dest with a directory where you want me to write the output to. I picked the VM. I want the minimal VM. That's that small VM that I talked about. And you tell me which profile you want. So this will just give you the smallest VM with compact 1. Well, by default, if you tell me I want compact 1, you're going to get the minimal VM anyway, because we assume that if you want small, you're going to get small. But you can override that. If you want to run the server VM with profile 1, just put server in there instead. Or if you want all the VMs so that you can run Java-server or Java-client, you would do -VM all, and we'll put out all the VMs into the Java runtime. So here's the example of the server VM. You would run JRE create, my full JRE, -profile full JRE, you'll get every class that's in Java JDK 8. And -VM server tells me you just want me to create the server VM. Ouch, I knew I was going to step on that. So let me try to do a demonstration now of the JRE create. Try to get my font as big as possible here. Now I'm running this on a Mac. You can run JRE create on any platform that has a Java runtime. JRE create is a Java program. I'm going to build an eJDK for ARM. If I go in the bin directory, you see JRE create, that's a properties file that has information that we need to run the program. There's a JRE create shell script that actually runs Java with the JRE create jar file. And if I just hit return, it basically gives you the help screen, the information that you saw earlier. Now if I want to write out, let's say I want to do a compact 2. Compact 2, so I say write it out to comp2 directory, --profile compact 2. Oops, can't spell. And let's see what happens here. Oops. Can't spell. All right, so it tells you what it's going to do. Its directory is this. In the ARM set of binaries, so it's going to do an ARM VFP version. It's selected the minimal VM by default. On compact 1 or 2, since they're fairly small, we just decided by default we're going to give you the smallest VM. And you're not going to have debugging. You're not going to have any of the debugging information in the class files. I'm not doing a dry run, and I'm not giving you lots of extra stuff, and there are no extensions. But if I want to, let's do a comp2, and I want the server VM. Let's put that in comp2 server directory. Let's override that. Well, and as you saw, compact 2 is 14 megabytes. It tells you the size that it's going to be created. So -VM server. Now I'm creating, with the server VM, you notice the size goes up considerably because the server VM is much bigger. So that's pretty much how you would run JRE create. Let's build an x86 version. I just want to show you that, the version string, and I should have had this warmed up, sorry. This is a Linux 10.10 virtual machine running on my Mac. So I can generate an x86 Java runtime and actually run it on the same machine because it is an x86 device. Okay. Oops, wrong way. I had this set for high resolution. All right, so let's see. So I'm in a directory that I labeled x86, so I know that I'm generating the binaries that can be executed here. JRE create dash dash dash. Let's do a compact 1 dash profile 1. And here again, we're generating the minimal VM, and it's a little more than 10 megabytes in size. So if I go into the compact 1 directory, I see I've got a bin and a lib directory, and in the bin directory, all I have is Java, small Java program. So let's go in there and do a Java-version. And you probably can't see it because I didn't stretch the window enough, but it's so you can see that in the top line, we're identifying the profile as compact 1 that we're running, and the VM is identifying itself as the minimal VM. So this is the small 10 megabyte compact 1 that you would run on your embedded device. So that's our tool for JRE Create. I'm now going to move on to give you a brief overview of the new stack. Since we don't have AWT Swing available in any of the lower tiers, if you want to build a graphical embedded application, we're providing you with a new graphical stack that's a more modern stack based on the JavaFX scene graph implementation. It will allow you to have high quality graphics on a small embedded device with much lower resource consumption. And it'll provide you with a common graphical API that you'll be able to run an application on a desktop, a Mac, Windows, or Linux, and also on a small embedded device. It's the same graphics, same APIs that you would use on your desktop. One really great thing that's needed in the embedded market is hardware acceleration using GPUs. I'm going to give you a demonstration just to show you the benefit that the GPU does provide. It doesn't have any dependencies on AWT and Swing. The UI is scaled down for smaller screen sizes. We've added touch support, since that's important for printers and other devices, and a pop-up virtual keyboard. We'll use platform media decoding for playing any media, video clips or audio. And the great thing is that it's only 6 megabytes of static footprint in order to provide this rich graphical stack. Just to show you, contrast where we were before. We had compact profiles with this new embedded stack. On the left, we have 52 megabytes for our headful ARM stack. And all that size comes from the SE runtime that we had. The VM is larger. The native toolkit, the X libraries, even the platform has additional requirements. We were requiring an X server, and then typically you would have a window manager. All of these things take up disk space and memory footprint. And the new embedded stack, all we have is our compact 1 profile. If you want the smallest implementation, we have our minimal VM, that 3 meg or less, and the JavaFX runtime. And that all will fit in 16 megabytes. So that's a considerable savings of disk footprint for your graphics stack. Our reference board for the first release is the BeagleBoard XM. We have 3 other boards that we're working with and trying to validate, but the initial release will only be on the BeagleBoard. There is actually an implementation on java.net for ARM devices for this BeagleBoard XM that you can download today and play around with. It's an early access, not for production use, but to give you some idea. If you look at these kiosks that are around the various hotels, you can play around with it, and that's basically this FX stack running on top of Java SE 7. We also have support for the Raspberry Pi, and I'm going to actually demonstrate the Raspberry Pi today. This great little device is only $35 if you have an Ethernet, or $25 if you eliminate the Ethernet. It's really inexpensive, ARM v6 processor with 256 megs of memory, Ethernet, GPIO, high def output, HDMI output, and it's really inexpensive and pretty powerful little device. We also are looking at Freescale IMX 5 series and 6 series boards, and the Panda board is actually the board that's running in these kiosks out here in the hall, that's running that scheduler app, and stop by and play around with one. That's SE Embedded running this graphics stack. This is the Raspberry Pi that I showed you, just in case you can't see from me waving it around. And let's see, so where are we going? in the future, so in SE7, we've reduced the JRE down 60% from a full JRE, and that has been around for a while. In JDK 8, coming out next year, we're going to have these profiles that I demonstrated for you to reduce the sizes. For JDK 9, we're going to be utilizing modules which will give you much more flexibility in terms of selecting the specific packages that you need rather than us having only 3 different smaller profiles for you to select from. So you'll have a lot more flexibility. If you happen to need a package that's up in tier 3 but you don't need everything else, today we still are somewhat rigid in terms of what you can deploy. In JDK 9 you will have a lot more flexibility. You can basically pick which VM you want, what modules you want, build up your solution using Jigsaw. Yes?
My question related to last few slides. Does the new graphics stack have functionality like feature like graphics 2D in the full JRE version?
Yes, if you take the full JRE, we still have the legacy Swing AWT graphic stack.
Okay.
Yeah, it's still there, but it requires the full JRE.
Okay, so it missing the full graphic 2D package there, or is that what you said? For the new graphic stack.
The new graphic stack has all imaging APIs, and I'll give you a demonstration in a minute as to what its capabilities are. You can basically do everything in FX that you could do in AWT and Swing and before.
Okay, because graphic 2D is enable the open EGL, low-level GPU, macro command processing, so things like that. This would improve the performance a lot because for my application, I need to render a lot of graphics.
Yes.
Based and computation.
Yes, FX is a much better implementation for embedded devices to take advantage of GPUs. For AWT and Swing, it requires the full OpenGL and does not run on top of OpenGL ES, the embedded subset. And for it to do that, you have Swing and AWT on top of Java 2D, on top of the OpenGL pipeline, plus it has its own pipeline. There's a lot of code in there, and utilize.
Everything in one
yes, everything all down to the 6 megabytes, and we're calling directly to the OpenGL GPU libraries. So it's much more efficient and better suited for embedded. As down here, our requirements are that you have an OpenGL ES library, and that's it. And we can draw directly to the library and the frame buffer. So we don't have XLib and an X rendering engine and then X on top of DRI on top of OpenGL. So we've cut down a lot of layers to make it more efficient for embedded devices. Yes?
Just a quick question. Obviously, with that diagram, you've got no XLib in there.
Correct.
So how does it deal with like mouse events and things like that? That kind of built into the website?
For mouse events, we're reading directly from dev input on Linux. There's a dev input mouse and dev input keyboard. There are actually multiple. We'll most likely be putting out at least some part of the sources so that people can adapt to different platforms at some point. Today we have multiple different rendering paths. There's a software renderer that doesn't even use the GPU. That all it needs is devfb. Maps into memory we write from Java and our native code. Then there's the EGL frame buffer, which is OpenGL required. You have to have OpenGL ES2. We don't support 1.1. And there's actually an implementation of EGL on X11. So if you have X and you want to run some other X applications, we have EGL that'll punch a hole through X and we'll go directly to the frame buffer. So, but all of the X11, of course, would increase your memory because X wants to keep backing stored. It's going to have a copy of the screen, so you're going to double the amount of memory you need. So the most efficient and high-performance solution that takes the least amount of memory is just EGL direct to OpenGL ES. I'll show you the frame buffer demo without OpenGL. Let me just close out on JDK 9, and I'm going to go over to the FX stuff before we run out of time. So in the future, Jigsaw will allow us to pick any one of these modules. This is a preliminary module list that is available in JDK 8. And I don't know if you saw the keynote. Mark demonstrated the fact that you can do JMod install of an application on an ARM device and it brings in all of the dependent modules automatically, so you don't have to worry about what the dependencies are. So it's a much better, cleaner, more robust solution for those folks that want to pick and choose just the modules that they want. But in the interim, at least, we're going to give you this 10 megabyte solution, which you don't have today, which is, I think, it's a great step forward. And we're also planning on providing a graphical tool, since there'll be so many things you can pick and choose among. If you want to, have the desktop APIs or the compiler or add Corba, we'll have this JRE Create GUI tool that will, in addition to a JRE Create command line tool like you saw for profiles, we're going to have one of those for JDK 9. We also have this graphical tool that we've been working on that lets you pick which VM do I want, which user interface do I want, headless, headful, the embedded FX stack, do I want debugging, do I want serviceability or JMX support? It will automatically pick those features out of the module library and build you a JRE that has those capabilities. So let me switch over now to give you a demonstration of JavaFX. Let me switch over. So I have one of these Raspberry Pis connected over here. I wanted to wave this around. It was harder to do with all the wires connected to it. But it's connected to the screen, and hopefully it's not going to go to sleep. So this is the Raspberry Pi after the kernel boot. So there's no X running, nothing. And I'm going to start up. I want to demonstrate the difference in performance between software rendering and using OpenGL ES. So let's do the software rendering first. So this is just a JavaFX bench program that I'm going to load up, and it's going to take an image and move it around the screen, and then it's going to go crisscross. So here you can see it's like kind of jerky. It's moving this flower picture around the screen, and I don't know if you can't see my screen, but it's basically reporting that we're getting 1.21 frames a second.
Bob, how did you run that? Is there a command line option to Java to do that?
Yeah, it's basically just Java dash jar.
No, to use software rendering versus.
Oh yeah, there's JavaFX.platform equals FB frame buffer.
Okay.
You just set a property. And so now I'm going to use the one that has the GPU.
Can you show the CPU usage for that case? Probably 100%.
It's most likely 100%.
Okay. Yeah.
A little different. Taking this image, let's see how many frames a second we have here. Come back. So we got 57 frames a second. So we're like 50 times faster taking this GPU, and I'll bet you the CPU utilization itself is much, much lower because the GPU is doing all this work. We're just saying, move this here, move this here. We take that image, we put it into the texture buffer, and we say, move it around. So that's pretty dramatic. Whoops. So now let's go beyond just a basic benchmark, and let's try to run something real. So in the demo grounds, there's an application of a printer, a simulation of a printer. They have a scanner connected to it. I'm using that same exact application here, but I've cut out all of the device, and we have a simulation set of frames that we're going to go through. It's designed such that it has a lot of really good interaction when the app is up and running. So it loads every image before, so it takes a few seconds to get going, but we should see it here in a sec. There it is. So here's the printer application that our team developed, just to give some idea of how you can take this small little embedded device and actually use it to drive the console of a printer. The tab at the top, this is actually designed for a touchscreen, so you're supposed to swipe to pull down, so I'm going to have to play around with the mouse a little bit to do that. So we can take a look at the supplies. Come on, pull it down. Okay. Come on. All right. So this gives you a simulation that we went out and queried the inkjet, how much ink is left, and you saw that the imaging and where it's drawing that. That's all JavaFX effects that we're doing there. Also shows you, we had some printer jobs and they've completed, and this one was canceled. We could also, see if the printer has the ability to put SD media and pick from a file Must have clicked it twice. But it has some nice animations to show you where you would actually plug the media in. It's a pretty slick little app, considering how much resources it has in the system. I also can simulate, actually doing a print. So we want to pick how many copies we want to do. Do we want a color or black and white? I pick color. So here's a simulation of what the printer might be doing. And this is all JavaFX running on this little device. And the JavaFX stack is a little more than 6 megabytes. We're still working on getting that down. It's like, I can show you the screen over here, exactly what I'm running here. So my JavaFX runtime that you would include in the JRE is actually right here, this lib directory. If I do a du-ks of lib, so I don't have a lot of junk in there, we're like at like 8 megabytes, but I have every one of the rendering paths available. I've got the X11, the dummy frame buffer, and I've got the GPUs, and those things would save us about another megabyte. So we're at 7 megabytes now and still trying to shrink this down even further for our target. Yes?
Let's say you want to talk to the other devices through the parallel port or serial port.
Yes.
Even to the devices through the PCI bus. Can you do that in Java without using any wrapper, without using JNI?
If those devices are available as a Linux kernel driver using Java I/O, you can certainly access those devices that way. But you need to be able to open a device and read and write from that device.
So let's say primitively communication protocol, something like RS-232. That's a very primitive. So can we do that in Java directly?
Yeah, today we have the comms API that we can use, and some of the demos on the show floor are showing that in use. For JDK 8, we're actually looking at other more sophisticated device APIs that you can add. They're not committed at this point, but we're investigating so that you'll have a full set. Yes?
Just to say, I'll talk about some of that a bit more in my Friday session tomorrow.
Okay.
I'll talk about some of the serial port stuff and things like that.
Okay, great. So that's about it for the demo. I'll just show you one more quick demo that I happen to have for those of you that are interested in possibly doing some gaming on this. One of the FX demonstration applications that happen to be there is Brick Breaker. So this is playing games on your Raspberry Pi. And I'm not very good at it, but well, helps hit the key. I don't know if you can even see the paddle on the screen.
Doesn't make sense very
Oh,
well.
yeah, it's chopped off on the bottom. Sorry about that. Oh well. Anyway, you can see I cranked up the performance, so it normally starts out really slow, and I didn't want you to get the impression that it's really slow. It's just the way the app is designed. So I sped it up. Anyway, that's gaming on the Raspberry Pi. Sorry it was chopped off a bit. So that's basically the end of my presentation. Open it up for questions. Just to summarize. I'll get my slides back. Just to summarize, with the introduction of compact profiles, we're providing you with a much smaller stack that we can hopefully target smaller and smaller embedded devices, and we're committed to continuing to push the envelope and get SE embedded as small as we possibly can. And so Duke wants to know if you have any questions.
This JavaFX packager, will this be working with this so you can create a compact application with everything, with the VM and everything too?
That's currently only targeted for desktop applications and not for embedded applications. Our assumption is that you would use this JRE create tool to create your application and bundle it together and deploy it yourself on your own media. And it's we're not going to enable FX downloads for embedded devices on the web or anything of that nature, because they tend to be closed systems, and so you will include FX yourself. And you can build it on NetBeans on a Linux x86 platform and produce the package, then bundle it with our JRE using the JRE create tool, and then push it off to your device.
Okay.
Any other questions?